Practical schemes to enhance vertical, horizontal, and platform reusability of verification components in Ember-based SoC design. This paper presents practical schemes to enhance the reusability of verification components for Ember-based SoC design verification. Ember Unified Verification System (AUVS) can reduce the amount of time to build test bench by predefining Ember agent per configuration, and it can also improve platform reusability of verification component by providing an abstraction layer of Ember VIP. Formula-like sequence FLS is a scheme to describe test sequence using an only tasks provided by hardware abstraction layer HAL, which positions itself between test sequence and agent, thereby enhancing the vertical and horizontal reusability of test sequences. Introduction. One research found out 20% and 23% of total verification time are spent on test bench buildup and test scenario coding respectively, while 36% on debugging time. In other words, in total amount of time for preparing for test, both test bench and test scenario is relatively greater than actual verification work hours, 45% and 36%. This is a good reason for why many efforts have been attempted to improve the reusability of verification components constituting the test bench and test cases. Among such efforts are System Verilog and the Universal Verification Methodology (UVM), which have boosted up such reusability. Although the System Verilog and the UVM can facilitate a design verification environment by providing basic verification components and methodologies, they do not guarantee the usability of such verification component. Rather, the usability can be improved by verification engineers only if they use or create such verification component with the concept of reusability in mind. The reusability can be categorized into three kinds: vertical, horizontal, and platform reusability. This paper presents practical schemes to improve all three kinds of reusability of verification component, aiming at Ember-based SoC design that is a general form of SoC. The practical scheme is composed of two major concepts. One, Ember Unified Verification System (AUVS), not only to improve verification component platform reusability, but also to shorten test bench build-up time. The formula-like sequence FLS to improve test sequences, vertical and horizontal reusability by providing hardware abstraction layer HAL between test sequence and agent. 2. Reuse problem. This section summarized three major reuse issues in the verification engineers encounter and find time-consuming while at work. Before introducing you to our suggested solutions. Problem 1. Test bench build. At IP block level verification, we need nearly as test benches as number of IP blocks. Each test bench buildup is considered as a series of routine jobs: agent creation and their configuration, interfaces creation and their configuration, verification component connection, sequences creation, and so on. If there were a simple and systematic way to do so, it would be a good benefit in reducing a great amount of time and effort put in building up test benches. Problem 2. Platform reusability of the test sequences. We might need to multiple vendors, Ember VIP for many regions, and including VIP license issues, co-emulator synthesizability, simulator compatibility, and even use of in-house VIPs. This situation enforces us to figure out how to effectively use different test sequences for each different VIP, so-called platform reusability issue. Problem 3. Vertical and horizontal reusability of test sequences. It is not unusual to see the cases wherein a sequence used at IP block level verification cannot be used at higher level for good reasons, including the different surrounding among the levels. As a result, Ember-based sequence used at IP block cannot be directly used at a higher level, so-called vertical reusability issue. Figure 1 shows an example of vertical reusability wherein AHB driver used at IP level cannot be used at subsystem level due to AXI bus. Similarly, we run into the similar issue when duty is reused in another project. For example, a software access port is changed from AHB to AXI. That's called horizontal reusability issue. In the following, Section 3 and 4 suggest separate solutions to reuse problem 1, 2, 3, and respectively. Section 3 introduces a UVS scheme, pre-built UVM-based verification platform with a wrapper agent for each bus protocol, which is devised to solve reuse problem 1 and 2 by reducing test bed build-up time and using wrapper agents independent of specific VIP. So in section 4, FLS scheme describes test sequence with only tasks of HAL is proposed is a solution to problem 3, and it makes test sequence free of SFR port protocols. IP block level test bench, subsystem level test bench, and figure 1 is an example of vertical reusability. Ember Unified Verification System, AUVS. AUVS overview figure to show the overall architecture of Ember Unified Verification System composed of AUVS TPI sequence, AUVS environment, and AUVS harness. The AUVS can be considered a built UVM-based verification platform which provides users with a reusable Ember transaction generation mechanism. Three major components are briefly introduced in this section, followed by more detailed explanation along the code snippets in the later sections. AUVS environment creates, configures, and connects AUVS agent. There are AUVS agents for each bus protocol, AXI, AHB, and APB, and each of them contains various vendors Ember VIP's agent. Users can select a specific vendor VIP and the number of each instances and other protocol parameters for the AUV's agent. Once the AUV's agents are created and configured, they are connected to AUVS interface. AUVS harness generates an array of AUVS interfaces per user's configuration and registers them in UVM resource pool so that the AUVS environment can fetch them whenever needed. As a result, all the Ember agent, any kind and any number, can be available simply by instantiating this AUVS environment with the proper user configuration, thereby reducing the test bench build-up time dramatically. Problem 1. Besides, You don't need to separate configuration classes to pass bus protocol parameters down to the agent. Parameters down to agent. Since the AUVS interface contains the parameters inside. This approach makes a little more sense in that such parameters are relevant to each bus protocol, although they are assigned default values. They can be overridden by user-specific values from outside later if needed. The Figure 2 AUVS architecture. TPI stands for Test Programming Interface. TPI is a class inheriting UVM sequence intended to provide all test sequences with the Application Programming Interface API to access VIP vendor independent EMBA transactions. The goal is to reuse a test sequence inheriting TPI without any modification even when a target EMBA VIP changes, thereby solving so-called platform reusability issues of test sequences problem 2. Since AUVS environment is a pre-built platform, all you have to is to use AUVS interface and AUVS TPI sequence properly. The following two sections will explain how they work from a user point of view, starting from the AUVS interface. In this paper, example code, it is assumed that a synopsis AMBA SVT, Mentor AMBA QR VIP, and in-house AMBA VIP sermon target AMBA VIP candidate. It is not to waste unnecessary VIP licenses to choose which VIP for use at compile time. B. AUVS interface. There are a pair of AUVS interfaces per bus protocol. Master and slave, snippet 1 shows AXI master interface code as example. Various vendors' AXI VIP interfaces are pre-built-in and connected, and so one of them will be chosen with defined at compile time. Bus protocol specific parameters such as address underscore width and data underscore width are defined and assigned default value as mentioned previously. The parameters are referred to by AUVS environment in order to configure AUVS agent. Snippet 1 AUVS underscore AXI master interface.sv. C. AUVS harness. Snippet 2 shows AUVS harness, a collection of all available EMBA interface. The interface are instantiated, assigned to a virtual interface, and then registered into UVM resource pool so that the test bench can fetch them through UVM underscore config underscore db ::get. AUVS harness can be accessed using include in test bench because interface is not allowed to inherit in the system variable. See snippet 7 for this. The snippet 2 AUVS underscore harness.svi. That D TPI sequence. Snippet 3 shows the header part of the TPI sequence class. And a TPI sequence class provides a pair of the write and read task of each bus protocol with which is inherited task sequences can generate bus traffic. The task communicate transaction, input and output data through argument. Argument AGT underscore ID selects a target agent among the many available ones. As before, picks up the AXI write task. AXI underscore write as the example to explain how it works. The code showed the case in the synopsis AXI VIP is chosen at target agent. As explained in the comment in the snippet 4, A vendor-specific sequence, item, and transaction is generated set with input argument configured with port timing values and then issued. Such a vendor-specific flow is pre-built in each TPI task. Snippet 3, AUVS underscore TPI underscore sequence.sv header part. Snippet 4, AUVS underscore TPI underscore sequence AXI underscore write body part. E, AUVS environment. In fact, it's enough to refer to the AUVS interface and TPI sequence explained up to now for users in order to fully utilize AUVS. The following two sections deep dive into AUVS environment, the underneath engine, to make all this possible so that one can understand how AUVS interface and TPI sequence are handled internally. As shown in snippet 5, AUVS environment has agent AUVS underscore AXI underscore master underscore agent configs AUVS underscore AXI underscore config virtual interfaces AUX underscore AXI underscore master underscore interface and virtual sequencer AUVS underscore sequence as a member. During build phase, all kinds of Ember protocols, master and slave agent are created along with their configs, followed by a routine of a virtual interface retrieval from the UVM resources DB. Agent configs configuration and data registration of AUVS virtual sequencer. AUVS sequencer. Snippet 5 only shows the AXI master case and an example, but other bus protocols should look similar. The sequencer of each agent is connected to AUVS virtual sequencer, AUVS underscore sequencer during the connect phase so that the TPI sequence can use it to put sequence in items into a specific agent later. Next comes AUVS agent 2, which is the most important component in AUVS environment. Snippet 5, AUVS underscore EMB.sv. F, AUVS agent. Snippet 6 shows AUVS AXI master agent as example, among other AUVS agent. This AUVS agent plays as a placeholder to contain a user-selected agent in each sequencer. The target agent is created and then the assigned configuration or config instance passed down by AUVS environment during build phase. During the connect phase, the target agent sequencer is connected to AUVS agent sequencer instead of AUVS AXI sequencer. In turn, is connected to the virtual sequencer of AUVS environment instance of AUVS sequencer as seen in the snippet 5. TPI sequence can utilize the target agent sequencer in this mechanism, which connected target agent, AUVS agent, and AUVS environment, and TPI all together in terms of sequence and sequencer. Snippet 6, AUVS underscore AXI underscore master underscore agent.sv. G, testament implementation. Up to this point, we've seen how AUVS is constructed and how it works, from TPI down to the AUVS interface. Now it is time to show how to use them in a practical way. Please recall there are only two areas to focus on from a user's point of view: AUVS interface and TPI sequence. Snippet 7 presented the example test bench module TP underscore top to deal with the AUVS interface. The module includes AUVS underscore harness.svi file for reusing AUVS harness and connect porch of the DUT to embed agent interfaces of the UVS harness. Connection between the DUT and the UVS environment is finalized by assigning the embed agent to configure parameters to corresponding interfaces. Snippet 7 tb_top.sv. Snippet 8 shows the example code of a UVS test sequence handling TPI sequence. This sequence inherits a UVS_TPI_ sequence and describes the test scenarios by using TPI sequence provided API tasks. Note that in pre_body, a UVS sequencer registers in UVM resource pool is assigned to a UVS_sequencer SEQR, a member of a UVS_TPI sequence. This mechanism makes it possible to continue to reuse a UVS_sample_ sequence based on API tasks, even though underneath embed VIP agent change. Snippet 8 AUVS_sample_sequence.sv. 4. Firmware like sequences FSR with a hardware abstraction layer HAL scheme. FLS overview. Firmware like sequence FLS is a sequence which enables to create a test sequence through harness abstraction layer. HAR is a verification component which provides API tasks abstracting DUT's feature. Such API tasks are written solely with the driver task, write_driver and read_driver to access DUT's SS file. The driver tasks use omni address and data just like memory mapped to block access typically used in firmware programming. In turn, write_driver and read driver call virtual tasks, bus write and bus read respectively, which allows specific or VIP independent implementation later, since bus operation over HAL are decided through the callback. HAR-based task sequences can be reused even if the SFR port protocols change, achieving a vertical and horizontal reuse. Problem 3. Figure 3 shows the overall architecture of FSR. You can notice that the upper section WRT will relate to HAR as protocol independent, while the lower is protocol dependent. Let us explain how FSR major components behave in the following section. In the figure 3, FSR architecture. B. HAR-based class and a HAR callback-based class. Snippet 9 shows HAR_base, HAR-based class, which is superclass to all HAR classes. Base R callback class, HAR_callback base is registered as callback class for HAR_base. HAR base contains two driver tasks, write drivers and read drivers. Each of them calls a virtual task of HAR_callback base, bus write and bus read. Snippet 10 shows the code of HAR callback base class. A task declared virtual is expected to be implemented with a specific embed protocol operation. Snippet 9 HAR_base.sv. Snippet 10 HAR_callback_base.sv. C. Test bench implementation. In this section, let us show how to HAR-based classes in creating VIP independent sequences. DDR SDRAM host controller, aka DDR controller, is picked up for this purpose. Snippet 11 shows a DDR controller's HAR HAL class, DDRC_HAR, by inheriting the HAR base class, or HAR_base.DDRC_HAL provides a API tasks which abstract the DDR controller's basic features. Note that those API tasks should be written in only the hard-based tasks, write drivers and read drivers in this example, so that the DDRC underscore HAR can be independent of specific bus protocols. The specific protocol for use can be defined in DDR controller's HAR callback class as seen in snippet 12. In this example, AHB protocol is used to write to or read from SFR. You can notice that a virtual tasks declared in HAR underscore callback underscore base snippet 10 are finally implemented in DDRC underscore HAR underscore callback class. Of course, you can change the tasks, for example, from AHB to AXI later in a different level test bench, vertically use, or in a different project, horizontally use. The snippet 13 is the code that replaces DDRC hard callback bus tasks if the test bench becomes to use AXI bus protocol for SFR access. The same thing applies to a case of the using RAL register abstraction layer. It's good enough for you to use RAR operations in those bus desks in the case. Once DDR controllers HAR and HAR callback classes are ready, the sequences can be written by using HAR API tasks as seen in snippet 14. Snippet 11 DDRC underscore HAR.SV. Snippet 12 DDRC underscore HAR underscore callback SV. Snippet 13 is AXI bus operation tasks. Snippet 14 is DDRC underscore sample underscore sequence.sv. In summary, FLS schemes allows us to create a test sequences dependent on the specific SFR port protocols by using hard API tasks. Since of the operation tasks underneath APIs are implemented in form of a callback, HARC reusability is guaranteed simply by changing such bus operational tasks even if the SFR port protocol change. Conclusion. This paper classified reuse problems which SOC verification engineers can easily encounter on the job into three groups: test bench rebuild, platform reusability of test sequences, and vertical and horizontal reusability of test sequences. In the following, a couple of separate critical schemes as solution to those problems presented to improve the reusability of a verification component in order to reduce the total number of total amount of Ember-based SOC verification time. First, Ember Unified Verification System (AUVS) provides a pre-configured Ember verification platform and a VIP independent Ember transaction generation mechanism. This adoption of AUVS helps users to reduce test bench buildup time, problem 1, and remove test sequences dependency on VIPs, problem 2. Second, firmware-like sequence as FLS is a hard-based scheme. In order to reduce the test sequences, even if the SFR port protocol change, by describing the test sequences through HAR, problem 3. Applying both AUVS and FSR together, it is expected to achieve the reusability of verification component in all aspects, vertical and horizontal and platform, which means that the verification engineers can be more likely to be concentrated on actual verification work itself rather than preparing for test by dramatically saving time and effort put in test bench build previously. Okay, thank you. for your time. Today I read this paper, Practical Schemes to Enhance Vertical, Horizontal, and Platform Reusability of Verification Component in Ember-based associated design. Thank you for your time and see you next time.